This is Li Yudi from Zhejiang University. I'm a PhD student working with Professor Tong². It's my honor to be here as a presenter of our paper Enclosed, predicting 3D closed deformation with mesh-based networks. As we all know, in past decades, closed simulation is widely used in many applications, such as games, films, and virtual try-on. It's challenging to obtain the fine results of the closed deformation. Traditional methods regard closed as meshes composed by many triangles and use physics-based models to update the vertices of the closed mesh. However, this process is quite time-consuming. To overcome this issue, some researchers tend to use GPU for acceleration. Tong et al. Proposed iClose in 2018 and used a single GPU to accelerate the simulation. Li et al. Proposed pClose in 2020 and used multi-GPUs to parallelize the simulation. Huang et al. Used GPU to generate wrinkles at submillimeter levels on the input closed mesh. The speedups are remarkable. However, there is still bottleneck to enhance the acceleration with a single GPU or multi-GPUs, and to achieve the fine acceleration, expertise is necessary about GPU algorithms and physics-based animation. With the success of deep learning in many fields, more and more researchers tend to use learning-based methods to seek a better solution. Loper et al. Proposed the SMPL model to represent the human body with shape parameters and pose parameters. Based on SMPL model, some researchers proposed new methods to predict the closed deformation with the human model. Patel et al. Proposed TiloNet in 2020 to model the closed mesh as a submesh and to deform the closed vertices with the skin human skeleton. Sachs-Stubben et al. Modeled the closed deformation as a skin transformation from the T-pose closed mesh, and the skin transformation is based for SMPL model. In 2021, they introduced a self-supervised method to handle the collision between clothes and the human body, and these methods obtain nice results of the closed deformation. But since these methods are designed for SMPL model, they are hard to apply to other human bodies which are not based SMPL model. There are also many researchers used other methods to explore the application of learning-based methods in closed deformation. These methods are not limited to the SMPL model. Gandaldu et al. Proposed GARNet in 2019 to use graph convolutional networks to predict the difference between predeformed closed mesh and the ground truth. Since using LBS to generate the predeformation of the clothes as the initial stage, this method is limited to tight garment. Holden et al. Proposed a method to find the relations between clothes and obstacle in subspace to predict the deformation. Unfortunately, they use the previous prediction as the input to generate the subsequent results. This will accumulate the error of the prediction. Huang et al. Proposed a learning-based method in intrinsic space to interpolate frames between separate poles. They only use the vertex features of the closed mesh without the topology. and their method is limited to human body with skeleton. So, in our paper, we turned to find a model. This model can process many different targets, such as human bodies and rigid obstacles, and this model is not limited to SMPL model. In addition, this model will not accumulate error of prediction and can use topology information to enhance the results. And we proposed our method enclosed, as we see in this video. The main results of our method are as follows. Firstly, we proposed a novel mesh-based method for interactive prediction of 3D closed deformation. Secondly, our method is an enhanced encoder-decoder network, neural network architecture. Thirdly, our approach can generate plausible simulation results at an interactive rate, such as 30 to 45 FPS on an NVIDIA GPU. Lastly, our method has up to 200 to 300 speedups over prior CPU-based and up to 8 to 10 speedups over GPU-based physics-based simulators. And the benefits of our methods are as follows. The input of our network is general. We can process many different obstacle meshes, including human and non-human meshes, and different closed meshes with various steps. Unlike the method of the Yang³ proposed in 2019, need to pre-deform the closed mesh using skinning methods such as LBS, our method has no need of the pre-processing. Our method is interactive and the results are satisfying. Our method can also handle closed meshes with up to 100,000 triangles. So, in our method, closed mesh is represented as many small triangles. This data structure is similar to a graph which is composed by nodes and edges. These edges connect the nodes of the whole graph, so the mesh information can be represented as vertex positions and edge indices. Then we input the vertex positions and edge indices to the closed mesh into the closed mesh into the graph convolutional network to extract vertex features. To enhance the connectivity of the graph, we compute the second order of the neighbors of each vertex to update the adjacent matrix. Then we perform the pooling operation on the graph and continue to use graph convolutional network to extract features. In this way, we obtain the vertex attributes of the graph. Here, we mark these layers as a network module. And we organize many network modules to compose the network closed encoder. We input the initial closed mesh and can obtain closed features IC in the intrinsic space. So we can obtain the closed branch of our network. Similarly, we can input the target pose human body mesh and target obstacle mesh to the network obstacle encoder and obtain the obstacle features I/O in the intrinsic space. In the intrinsic space, closed features IC will send to a set of linear fusion functions F. Obstacle features I/O are used as weights to fusion these linear fusion functions in intrinsic space. The parameters of these linear fusion functions are optimized during training. After the fusion, we obtain the target closed features at T in intrinsic space. Then, target closed features at T is processed by network closed decoder to generate the deformed target close. During this process, we add connections between obstacle encoder and closed decoder. The output of each layer in obstacle encoder will be sent into a linear network and then be added onto the input of each layer in closed decoder. We do this to add more impacts of the obstacle to the deformed close. After all this process, the final output is a deformed close mesh on the target obstacle. So, the whole network is marked in the rectangle. The input is the initial close mesh and the target obstacle mesh. The output is a target deformed close mesh. We download many different poses of different human bodies from the website Mishamo. Then we extract OBJ meshes from these sequences and use closed simulator ArcSim to produce deformed close meshes. Here, we obtain several results of prediction on the test data. In this scene, we can see that close mesh has 16,000 triangles and the obstacle bunny has 12,000 triangles. We show the results of prediction on the test obstacle mesh. The obstacle bunnies are with different positions, rotations, and scales which are unseen during training. Our network can handle different types of clothes. As shown in the picture, the dress has 16,000 triangles. The jacket has 10,000 triangles. The t-shirt has 12,000 triangles, and the pants has 18,000 triangles. We can see that our network can produce Feng predictions on the test data for different types of clothes. These are jacket predictions, and these are dress predictions. Our network can also process different bodies. The kid, Andy, has 33.8 thousand triangles. The man named Q-man has 14.6 thousand triangles. And we also extract SMPM bodies from Telonet, which have 55,000 triangles. We can see that the predictions on Andy and the Q-man are satisfying. We also show the comparison of prediction between our method and Telonet, and our results are convincing. We also show the results of different resolution. The rope has 20,000 triangles or 100,000 triangles. We show the comparison between our network and Telonet. We can see that the results of our network are with very high accuracy, the errors between our prediction and the ground truth are quite small, and the prediction of our network can reserve fine deformation details. We also compare the runtime between our method and the GPU-based closed simulator, iClose. We can see that the prediction of our method is faster than iClose, and the time of prediction is stable using our method. In conclusion, we obtain plausible closed deformation results on complex benchmarks and achieve constant frame rates on complex benchmarks. To the best of our knowledge, our method is the first learning-based closed deformation method that can handle arbitrary closed meshes and obstacles, and we achieve considerable speedups over prior CPU-based or GPU-based closed simulator. However, there are little limitations in our method. It's hard to provide rigorous guarantees using learning methods. Thanks.